Hello, everyone. Thank you for tuning in. I'm Gaetano Panagia, Technical Marketing Engineer with Hamamatsu Photonics Europe. And today I want to talk about miniaturized UV visible spectrometers and how they are enabling real-time water quality monitoring. So first of all, let me give you a brief outline of my talk for today. I will start introducing the challenge of water supply worldwide. Then I will talk about current methods for water quality monitoring, focusing specifically on optical methods. And among these optical methods, we will distinguish among single wavelength and multi-wavelength analysis. And finally, I will introduce the most anticipated UV spectrometer from Hamamatsu Photonics. In the end, I will also talk about illumination available for UV spectroscopy, and we will also go beyond water quality analysis, talking about another interesting application. But let's start right away with the introduction of the challenge of water supply worldwide. It is estimated that 3.4 million people die every year because of waterborne disease. And just to give you an idea, this is the size of a city like Berlin. On the other end, more than 80% of the wastewater processed by factories or similar entities is released back into streams without any proper treatment. So to face this challenge of water supply, there is mainly two reasons why we want to monitor water quality. One, it is already mentioned, is wastewater monitoring, because polluting entities need to comply with regulations whenever putting back water into streams. And the other one is to ensure that we always have the safest drinking water coming out of our tap. So for these two kind of application fields, we have several methods for water analysis. And the traditional ones are mainly two. One is the chemical water analysis, and the other one is biological. When we talk about chemical, there is two main methods. One is electrochemical analysis, and the other one is titration, while biological analysis uses bacteria to monitor the water quality. But these methods, they have some drawbacks. So the first drawback, kind of obvious one, it is the sampling to results time, which is very long when you consider that a sample needs to be collected, then it needs to be shipped to a specialized lab, and here it is analyzed before you can get your results in days, sometimes even weeks. So it is a problem, especially when you want to react immediately. For example, if you think about monitoring drinking water quality from our taps, if there is an accident that compromises the quality of water, then you would want to react as quick as possible, and you cannot afford to wait for days. Second drawback of this kind of methods is that they require extremely expensive equipment, bulky equipment, but most of all, they need specialized personnel, which is not always available anywhere at any time. And finally, these methods, they require the use of some reagents, and they can be polluting themselves, so they can cause some secondary pollution. The alternative to these traditional methods, it's a physical method, or in other words, a photonics method. So we use light to determine the water quality. This method is pretty well established, and I'm going to describe it briefly. So you have broadband light source on one side, which emits at a certain intensity in several different wavelengths. Then you have a sample, which is through which this light travels through. And then at the other side, some light is transmitted, and this light now contains the spectrum, contains the fingerprint of the specific fingerprint of the chemicals that are dissolved into it. So the intensity of the light coming out of the sample is going to be reduced only on some of the wavelengths, so we can analyze them using a spectrometer to understand the composition of the sample itself. So inside a spectrometer, then there is some optical components that will split the wavelengths, the broadband light into each wavelength component, which is then focused into a linear image sensor, and that gives us the possibility to understand what's the intensity at each light frequency. And this whole process is regulated or is described by Lambert-Beer's law, which quantifies one parameter, which is the absorbance of the sample. So this absorbance can be described by three main factors. One is the molar absorptivity, which is peculiar to the specific chemicals dissolved into the sample. Then you have the path length, which is actually the length that light needs to cross through the sample. And then the most important is concentration. So this tells us that with this method, we can not only detect that a specific chemical or a specific chemical is present in this water sample, but we can also determine how much of it is in there. What are the advantages of such method? One is obviously that you can do real-time and on-site measurement. So as you will see in the following part of my presentation, the size of these devices is so small that they can be deployed really anywhere pretty conveniently. And then they can also be connected to deliver the information very far from the site in which the measurement happened. Another advantage is that this method does not need any filtration in general, and we will see about that as well. Plus, there is no need for any polluting reagents. In fact, with this method, we never touch the sample itself, so we never physically interact with it. We just have a light interaction. We never need to mix anything with it. And the talk today focuses on UV visible spectrometry. So you might be wondering, why do we need a UV spectrum to do this analysis? And in this slide, you may find your answer. In fact, there is some traditional parameters that are measured with those traditional methods that I mentioned at the beginning. And these methods they can be best measured in using UV spectroscopy in the UV range. So we're talking about TOC, total oxygen content, DOC, dissolved organic content, and even the presence of disinfectant. Then there is other parameters like NO2 or NO3 that are often measured for water quality analysis that find their absorption peaks in the UV range around 250 nanometers. Plus, we also want to have some information about the visible spectrum, because that's where we can measure the turbidity of the water that we are analyzing. So this means that we can compensate for turbidity, and this in turn means also that we can deploy this kind of detectors anywhere, regardless of location and water clearness. But let's move into describing the two main methods within the optical method. So two main optical methods for water quality analysis. The first one is a single wavelength analysis. So we still have broadband light. Does not need to be as broadband as the multi-wavelength, because anyway we are focusing only on one specific wavelength. So we have light emission, the light goes through the sample again. Then we have a bandpass filter, whose passing band is the same absorption peak of the chemical that we want to measure. So, for example, we want to measure total nitrogen, or we want to measure COD, BOD, nitrate, this kind of samples. Each of them can be measured at a specific wavelength. So we will tune the bandpass filter according to the parameter, according to the analyte that we want to detect. And for doing that, we need a photodiode responsive in the UV or in the visible. And this is generally a silicon photodiode, like the ones that you're seeing on the right side of this slide. And you can notice from the drawing that they are extremely small, having a diameter below 10 millimeters. The advantages of such methods are easy to explain. It is extremely simple design, and as we saw, the footprint is particularly small. On the other side, you have information only on one single wavelength, and the accuracy of the measurement can vary according to some external factors, for example, temperature, and it's difficult to compensate for turbidity, which, as we saw, is generally done using the visible spectrum. So having information about the visible spectrum, but in general, having information about many wavelengths. On the other side, we have the multi-wavelength analysis that we saw 2 slides ago that use a spectrometer instead. And this have several advantages. So obviously, we are now analyzing several different wavelengths, so you get a comprehensive analysis using some software processing. You can get information about several analytes present at the same time. The footprint is still extremely compact, and you will see that in the next slide. And we can do particle compensation or turbidity compensation using the visible part of the spectrum. So in general, with multi-wavelength analysis, we achieve higher accuracy and a more repeatable measurement. And here is the looks of our new UV spectrometer, which is called C16767MA. This form factor is not new to Hamamatsu. In fact, we have been selling the visible counterpart for many years now, specifically for colorimetry, for example. And now we added this new device, which has sensitivity between 190 and 400 nanometers, which, as you see in the graph below, it's extremely compatible with those parameters that are useful for water quality analysis. And these devices are very unique because they use all our expertise in the MEMS production, which allow us to create diffractive grading into very tight spaces, and we can play then with the optical design to make these devices as powerful, so small, and also so powerful at the same time. And here you can see some characteristics of this new UV spectrometer. We've talked about size. You can see that the long side of this product is about 20 millimeters, so extremely small, size of a fingertip. You can see the spectral response, which goes from about 190 nanometers up to 440. Spectral resolution is outstanding and compatible with many of these applications. We're talking typically about 5 nanometers. Signal-to-noise ratio, very important to detect a low concentration of analytes in water, is 291 to 1, so pretty good. We have a dynamic range of 5,000. And then we already talked about the small size of the device, but then we decided also to include an electronic shutter function into the system, and this is for synchronization with light sources, which when you use flashed light sources can also help in increasing the signal-to-noise ratio, especially when you use lock-in amplification. And then in general, this device is not only compact, but also uses or requires a very low power. This makes it perfect for the integration into portable devices that can be battery powered, so deployed into a remote area, and they can stay on for a very long time, requiring very little maintenance. But at Hamamatsu, we do not only offer detectors. In fact, before detectors, we offered lamps, which is a traditional technology that we've been supplying since a very long time. And specifically for these applications of water quality analysis, we talk about xenon flash lamps. So xenon flash lamps are glass or metal bulbs filled with high purity xenon, which emit a broadband light in a very short pulse. As you can see from this graph here, we have a wide selection range, especially in terms of wattage, but also in terms of modularity. So you can get a bare lamp if you want to integrate it into your system, but you can also get a module which is completed with a trigger socket and a power supply. These lamps, as I said, are chosen for their broadband emission, but they also offer long lifetime. We're talking about 10 to the power of 9 flashes before the performance starts to degrade, and also high output stability when it comes to light emission and also spatial stability. As you can see from the graph to the right, one of the main characteristics of these lamps is high emission in the UV, and this makes them perfect for the application that we're talking about today, so water quality monitoring. And so moved by the idea that at Hamamatsu we can supply detectors and emitters, our central research laboratory built a demo setup that you'll be able to see at many trade shows with us. And this includes the 2 watts xenon flash lamps and this new UV spectrometer that I mentioned. And this setup is used to analyze some vials in which we have water with dissolved pollutants, specifically nitric acid, BOD, and also we did an experiment comparing this setup with a larger benchtop spectrophotometer using 3 different concentrations of anthracene. And as you can see from the rightmost graphs, the peaks that we obtained were totally comparable. This means that you don't need an expensive, bulky device to carry a water quality monitoring application, but you can do that with a UV microspectrometer the size of your finger. And to help in the evaluation of such device, since this is an analog device that needs a control board for electronic board for control and readout, we also offer a specific evaluation circuit that can be used to evaluate the capabilities of this device. We've talked about xenon flash lamps as a light emitter, but I also wanted to mention deuterium lamps, which is another important product in our portfolio. Deuterium lamps, as you can see from the wavelength range to the right, they are also compatible with water quality analysis measurements, as they emit, again, in the same spectral range of sensitivity of our new UV spectrometer. They are extremely stable. We're talking 0.005% pp variation. They have a long lifetime of about 4,000 hours. And in this case, they can work in a continuous mode, so they do not need to be flashed. Again, compact design and pretty cheap as a solution. When we look at other possible detectors for water analysis applications, we already mentioned silicon photodiodes that have a good responsivity in the UV range that can be used, for example, to measure NO2, NO3, but also total nitrogen, for example. If you want to go in the near infrared instead, so you want to do your water analysis in the near infrared, where you can, for example, measure the total nitrogen content in a water sample between 590 and 1700 nanometers. Or if you want to measure the total phosphorus content that can be measured at 660 or 880 nanometers, you may want to consider using InGaAs PIN photodiode for single wavelength detection, or even InGaAs arrays that are linear image sensors with sensitivity in the near infrared, which can be used to perform near-infrared spectroscopy, as well as visible image sensors like CMOS and CCDs, which are renowned for being extremely valuable in spectroscopy, like in the integration into spectrophotometers. So in general, just to summarize, I want to point out that if you have a water analysis application, you most likely will find your solution, both in terms of emitter and detectors, at Hamamatsu Photonics. Finally, I want to go a little bit beyond water analysis, and I want to mention an application which is kind of related to water, but is different. In fact, there is a certain regulation imposed to large ships to monitor their emissions whenever they get into harbors. And these emissions are generally NOx, SO2, and NH3 emissions, so ammonia emissions. And we know that this can also be measured using UV visible spectroscopy. So this device that I presented, this compact UV spectrometer, can be a valuable tool as well for continuous emission monitoring in large ships. Finally, just a summary of my presentation for today. UV spectroscopy is enabling real-time water quality monitoring, something that could not be done before with the traditional methods. And UV visible wavelengths can be used to detect those same parameters that were traditionally measured using a lab and a bulky, expensive equipment. The new Hamamatsu compact UV spectrometer can change the game in water quality monitoring, specifically for its extremely small size that can be useful it can help to be deployed into water pipes, for example, or as we said, into portable instruments, battery-powered instruments. And finally, beyond the new compact UV spectrometer, Hamamatsu has a wide offer in terms of lamps for every kind of application, even beyond water quality analysis, as we saw. So thank you very much for your attention today, and I hope this was useful to you, and I will see you next time. Thank you.